So actually, we just had a very nice introduction to the MOC already last week, but I will do it again anyway and try to do it slightly different, but it's going to be basically the same thing. So, but getting to the objective, so why do we do this? Study the meridional structure of the MOC with a time series from observations. So we want to analyze the seasonal to interannual variability at several latitudes. And we care about that because the heat transport associated with the MOC can impact the heat storage, sea level rise, and air sea fluxes. And this in turn can have impact on regional climate, for example, in Europe. So, and then I found this nice sketch, which is basically the same sketch we saw before, just on the globe instead of on the map. So we have the warm water going north near the surface, and then it's sinking in the north. There's a heat loss to the atmosphere, and then it returns back to the south as relatively cold water after sinking to considerable depth, meaning North Atlantic deep water depths, like below 2,000 meters. And then, according to this paper, the heat transport between 24 and 26 north is about 1.3 petawatts. And that amount is roughly 25% of the total, meaning atmosphere and ocean, poleward heat transport. For example, Jones et al. Wrote that. And there's a strong transfer of heat from the ocean to the atmosphere in the subtropical North Atlantic, basically, in the mid-latitudes. And that results in a relatively temperate climate in northwestern Europe. And so if the AMOC changes, then it could reduce the amount of the heat carried north and thus impact the climate in northwestern Europe. And such changes could also affect the CO2 sink in the North Atlantic. There was a study on that. The position of the ITCZ, including the Atlantic storm track, rainfall rates, because if the ITCZ shifts, then the rainfall rates in various areas change. And also marine ecosystems will change because where the upwelling happens changes, for example. So a lot of impacts potentially. So then in this study, which summarized both models and observations, so the lines are models, it found that the largest meridional heat transport is at about 10 degrees north with about 1 to 1.4 petawatts. And depending on which data set or which model it comes from. And then the heat transport drops to about half of that, near 40 degrees north, which is due to that heat loss that I mentioned before to the atmosphere. And in this latitude range, so around 40, or in the overall latitude range here, the EIA, or the NSTEP 1 and EIA 15 both have a little bit lower transports than observation-based estimates. And then we saw this little sketch up there already from the CM 2.5 model, which had the upper cell of the MOC with about 15 sphere drops between 26 and 42 north. And then it had a pretty big, far north extending cell of the lower cell with a little bit more than 2 sphere drops. And then below here, that's the 4 latitudes that I used here. So it's 26, 27, 37, and 42. I'm also trying other latitudes, but I'm not getting good estimates. And so this is basically the same figure as the one above, but the full time series mean at those 4 latitudes, and I basically get like 16 to 18 sphere drops of MOC compared to the 15 up here. And the lower cell pretty much stops just about south of 27 north. So I don't get this northward Atlantic bottom water And Chris already said it doesn't go that far north, and we all know that. So, and to get this, I'm assuming mass balance, and I'm correcting for the Bering Strait through flow, the way Behringer and Garzoli did. I'm using that same approach. Then this is basically the Mocha rapid time series over here, the different components of it. And basically what they were trying to do is the trend that they see in the time series. So that's the solid line here. And they estimated the trend with and without this minimum in 2009, 2010. And so this strong minimum basically doubles the trend. That was the main message of that paper. So I'm not going to go into all the details of all the numbers. They did the components for the Gulf Stream. Maybe the most interesting part is the lower one. I think it's the lowest one. That the trend that they saw in the time series is largely due to the interior flow in the upper ocean. So, and then here's a different study that we actually also talked about in our AMOC discussion group. So this one took the total atmospheric approach of getting the MOC, and it came up with this time series in black. And it's more or less stable. So it has the same stronger wind here as the red one is Mocha Rapid again. And it does not have this trend here. And other than that, it looks relatively similar with the shorter periodic wiggles, but it's relatively stable. Of course, this is very much smooth. The relatively stable trend here doesn't exist in the other time series. And then here's again, they looked at in the state of the climate 2012, and pretty much the same was seen in the 2015 time series. So I just had to choose one of the two. So the mean in 2004 to 2011 was 17.5 Sverdrups. And then they had this 2009, 2010 trend where it was only 12.7 Sverdrups. And then they had in 2010, 11, they had a recovery to about 16.9 Sverdrups. And this study and others found that these shorter periodic drop-offs like here, this is 2012, I have to go down here. This is the 2009, 2010 event over here. Anyway, the shorter time events usually coincide with a lower Ekman transport, or sometimes also with a minimum of the Florida current transport. And then this event was preceded by this weakening over many years of the transport in the interior, which I mentioned before. So going back to the data I was using, so I used the Argo profiles, which are shown here, and they're more or less evenly distributed throughout the year. So there's a little increase towards the end of the year, but I don't buy that that's significant. And the trajectories are shown below, and they're also pretty much evenly distributed over time, seasonally at least, throughout 2000 to 2015. And from that, I derive synthetic dynamic heights. And then I did a climatology of the observed dynamic height from the Argo profiles and the synthetic dynamic height at 1,000 meters. And the one from Argo looks more noisy, but that's pretty much the only difference that I can see here. It looks very, very similar. So getting the synthetic dynamic heights works at least on the mean, and it also works for the temporary variability. It works pretty good, as we showed in the South Atlantic. So from that synthetic dynamic height, I then get the zonal and meridional velocity from geostrophic balance. And relative to a level of no motion at 1,000 meters in the top two panels, And then I use the trajectory data from Argo and other floats if I have any, and get the subsurface velocity at about 1,000 meters or wherever the floats drifted to do a geostrophic adjustment to get the adjusted velocity, which is shown in the lower two panels. And the main thing we see is an increase in the velocity both for the zonal and meridional component in the Gulf Stream, and not so much change everywhere else except here close to the equator, close to 20 north. We see a little bit of change here. So here it's all green, and here there's a little bit of blue and red. But the main change is in the Gulf Stream, which is not surprising. And then I have my velocity field, and of course there's a problem near the boundary. So, and the problem is it stops at 2,000 meter depth. So, oh, no, I did the same Sylvia and Chris did all the time. Okay. Anyway, so I have to pad with World Ocean Atlas where I don't have any observations, which means below 2,000 meters. And near the boundaries, I have to do some padding. And then at 26 to 27 north, I can do better at the boundary because I can actually use the cable data. And then at other latitudes, I don't have a special treatment. I don't have any long time series of observations of the velocity of the boundary currents. So I can only do it for the Florida cable, this adjustment. And then I estimate the transports assuming a Morse balance while allowing for the Bering Strait through flow. And in 26 to 27 north, I do not allow adjustment in the Florida current because we have the absolute transport. So I have to do the adjustment only in the component east of the islands. And then I use this to derive a monthly time series from 1993 to 2005 at a couple of latitudes, including 26, 26.5, and 27, and they pretty much are almost the same. So that's good. So I'm now going to focus on 26.5. So I actually got a daily time series, which is my first attempt to do that from the product, thanks to daily Aviso data. And we see pretty much that all these nice wiggles actually is easier to see in the next one. So this is the daily, and Mocha Rapid actually here, it's twice daily. And then the means are 15.2 for the Argo and altimetry time series and 17.3 for Mocha Rapid. So that's pretty close. The standard deviation is almost the same. And the heat transport is almost the same, including the standard deviation. And then there are the other observations from the slide that Molly put together. The one that had the latitude dependence of the transports, it was like 0.8 to 1.5. So both estimates are well in that range. And then here I have the black time series is basically an insignificant trend computed as a trend per decade. And then Mocha Rapid has this trend of minus 4.2, here the red one, for the Sverdrups, and 0.24 for the heat transport. And if I do the partial time series for the same time period, I get a much smaller trend. So that's kind of what I'm going to look at a little bit. Why would that be different? Now I also, here I compare the monthly time series. And what I'm seeing is here, here you can see it much better than in the daily. Those strong events here marked by arrows, they are present in both time series. So that's pretty good. So I both get the short-term events pretty decently the same way. And then we have this discrepancy where it seems to be almost flat here, and in Mocha Rapid has the trend here in this time period, 2005 to 2009. So I'll go to the next one. And then the Mocha Rapid fork split up the components as we saw in the State of the Ocean BAMS report. So I basically did the same thing for the Mocha, plotted the Mocha Rapid in gray for all the components. So green is the Florida current transport, which is pretty close to each other because we are both using the cable. So I have to look at why there's a slight difference, but I don't consider that difference very significant. Then this part is the total MOC, yeah, 15.3, and we see this, the filtered, or what looked like filtered line is actually annual means, and the other one is filtered with a 90-day filter, the wiggles. So here we see the trend in the annual means in the Mocha Rapid, and it's flat in the new product. This is the Ekman component, which agrees almost completely. And then this is the interior, where Mocha Rapid has this trend and we don't. And it looks pretty much the same for the heat transport. So we get the trend here, we get a little bit of a trend here. Ekman is almost the same, Florida current is almost the same. Okay, are you going to go to the next one now? Okay, thank you. So now I try to explore this a little bit more. And I know that both Mocha and Rapid and my product are using the mass balance. And I said, well, what happens if I don't apply the mass balance? I should stay away from this mouse. And so the blue is the mass balanced time series. And the red is no mass balance required. So, and then we get this wiggles around 0, and then we get this strong drop off here between 2002 to 2005 roughly. And then it goes back to wiggling around 0, and then there's another drop off here. And now behind this, which doesn't show up in the PDF, is actually the upper 600 meter component, which doesn't show anything like this. It's pretty much flat. So the first one here at 610 meters to 1,000 meters, we see a little bit of a drop off here. Between 1,000 and 2,000 meters, we see this drop off here. And then from 2,000 meters to the bottom, we also see the drop off here. And at the time when Mocha Rapid has the trend, we don't see a drop off. So that's 2005 to 2009 is when Mocha Rapid has the drop off, and we have nothing here. So I don't know yet what to make out of that. It's just kind of right now observing what's in the data set. And as it is, below 2,000 meters, everything I have is climatology. But it still somehow gets this trend. So I'm really like, what's this causing this? I mean, yes, you. So, so I have to look at that a little bit. I mean, I have to do some tricks to make this, to not have a jump at 2,000 meters. So I have to play a little bit with the dynamic height from levitors to make sure there is no weird velocity jump at 2,000 meters. But still, I have to look at that, what's happening here, but there's something interesting. Did I forget anything? Yeah, so, and for Mocha Rapid, one thought or hypothesis is that the trend they see, this longer term trend in 2005 to 2009, has to do with a density change in deep ocean near the western boundary due to a change in the formation of North Atlantic deep water with a reduced, for example, reduced density of Labrador seawater that started in the late 1990s. So there are some hypotheses what might be causing this, but I think this will need quite a bit of work to figure out what exactly is happening and how the mass balance plays into that when you try to get the overall integral. So, and the other thing I looked at is, okay, do I get the annual cycle? And so on the left is from the daily, and on the right is from the monthly time series. And so both show an annual cycle, but pretty much only starting in about 2002. Before that, there's not much of an annual cycle. And that's both in the volume transport and in the heat transport, the same thing. And then if you average it over the whole time series, you do get a significant annual cycle in both products, so, which is not surprising. They're both at the same latitude. So just here, because it's monthly, you get a little bit larger standard error, and here's daily, so you get a much smaller standard error. Come on, next. Thank you. And then I went to 37 north, which is one of the latitudes where it kind of works pretty well, but I do get a little bit lower transport than other observations here, 0.63 petawatt versus 0.85. But it's not too bad. And then I get some of these pretty strong drop-offs here. And so that, and also in the heat transport. But it's not so much different from Mocha Rapid, so, but this is monthly, not daily, so I want to look more closely what's happening here with these stronger drop-offs. And then that we get an annual cycle again, but not throughout the whole time period, both for the MOC and the heat transport. But then we get this funny thing over here, which I don't buy at all. So I have to look at that. Why is there a high energy here at like 8 years for the heat transport? So doesn't make any sense to me right now. And then I try to look at like 2 ocean indexes, the Nino 3.4 and the AMO. And pretty much neither one of them can explain the variability we are seeing. So this is a 1-year filter to focus on the interannual stuff. And so for the Nino, yeah, we have a strong El Nino here and we have a drop-off in the MOC, but we also have a strong El Nino here and nothing happens. And then we have another strong El Nino here and we have a drop-off. But it looks more like coincidence to me than any relationship. And for the AMO, it's just as bad, if not worse. So, and so now let me get to the conclusions. So we derived the mean transports in the upper cell at 4 latitudes in the subtropical North Atlantic that agrees quite well with other observations and our heat transports as well. So Mocha Rapid shows this trend in 2005 to 2009 that could not be reproduced by this Trenberth Fasullo study, who used this atmospheric fluxes to estimate it in the energy balance approach. And our new time series has similar means and standard deviations when compared with Mocha Rapid. It also has the short-term anomalies in the time series from Mocha Rapid. Here are the X4 that I marked on the pictures. There's a pretty strong annual cycle, and there's large interannual variability. It doesn't look like El Nino has anything to do with MOC large anomalies like the 2009-2010 event. It coincides, but other El Ninos didn't cause a drop-off like that. So that's the 1997, 1998 didn't do anything. The most recent strong El Nino has again no coincides with a weak MOC, but I don't think there's a relationship. So and the same for the AMO. And then the other part was pretty much, which is very much work in progress, is we cannot reproduce the 2005 to 2009 trend found in Mocha Rapid. And it's clearly visible in the Mocha Rapid time series in the upper ocean transports, but in the new time series, there are no such trends in the upper ocean transports. And then there's the hypothesis of the changes in the density structure in the North Atlantic deep water. And the new time series, of course, can't really resolve the North Atlantic deep water because it's all climatology below 2,000 meters. But still, if you have changes in the depth and they change the upper ocean transport, then it kind of should show up in the non-mass balance time series. So that's what I was trying to do. And I found something before the signal and not during the signal. So anyway, so this mass balance indicates that large trends of the corrections exist. So I had these like 30 square drops over a couple of years, or between 20 to 30 square drops, and then it went back to almost zero in the mass balance correction. And there's one period that had that was 4 years before the 4-year trend in Mocha Rapid, and then I think we just need more analysis to understand how to get a handle on that, what is really going on. There are also model studies, actually, which I didn't put in this presentation. Some models reproduce a trend in Mocha Rapid and others don't. And so I think that's really something that will be worked on for a couple of years, and we will maybe figure it out one day. And this is the end. Any questions? Yes.
Yeah. First of all, the velocities that you use to adjust the reference level, are those time being, or do they have temporal variation?
That is climatology. I don't have enough velocity to do a time series.
Understood. Yeah. So when you impose the constraint for mass balance, are you putting a constant velocity across the entire section, or are you multiplying those meridian velocities by some factor alpha?
Right now it's not weighted. Right now I'm doing what pretty much everybody else has been doing, which is a basin-wide mean.
Yeah, so that's what I'm getting at.
And the only thing where I was playing with weights was that I did not want to adjust the Florida current because it's actual accurate measurements. So, but in the interior, I would have to probably test models how you could do a longitude-dependent adjustment.
You could simply say, I'm going to multiply all of those reference velocities that I have from the flow trajectories by some coefficient alpha and find alpha that gives you the mass balance you want.
Right.
And then you'd be doing larger adjustments in the places where you already have existing large barotropic components, which would be a lot more realistic.
Yeah, that's a good idea. Yeah. We'll try that. Thank you.
Claudia,
yes.
Can you go back to your plot, like below 2,000 meters? Why the transport has large time variability before that? The right one is without mass balance?
The red one has no mass balance, yes.
Yeah, so because your reference velocity is a time mean, and your piling, so maximum you will have seasonal cycle. Well, there's probably not much below that. I think it's quarterly. Why you have such large variability?
You mean? Oh, did it again? You mean in this one? Right, the top panel, or below 2,000. Okay.
It's all climatology. That should be constant close.
Well, I mean, that's where I have to look what exactly is happening, because I'm using if I take the dynamic height from my velocity field and I take the dynamic height from World Ocean Atlas, they wouldn't necessarily match. So you want a smooth transition in the vertical profile. So whatever is in the dynamic height profile.
Everything's climatology, so I see.
Yeah.
Right.
It's just, I don't understand that part.
I mean, we can talk offline later, because it's going to take a little bit longer to explain how this is happening. I have to take a closer look at that as well, but I just know that, like, your dynamic height gradient at 2,000 meters changes and doesn't match the dynamic height gradient in the World Ocean Atlas. And so if you want a profile that looks like a clean dynamic height profile from top to bottom, you have to somehow manipulate the dynamic height profile from World Ocean Atlas. And I think that's what's going on here. Otherwise, you have a discontinuity at 2,000 meters, which is really weird. So if you were not doing just dynamic height, if you were padding with velocity, it might be different, but we are padding the dynamic height profiles. So that's certainly something interesting to look at. How does that impact the result? Let's see. What else do we have here? So looks like